Very good. All right, officially welcome everyone to Legumes in Space Live. We are here today to discuss our post-flight science observations so far based on what we have seen in the last week or so, couple weeks. And we wanted to show you some images and some video that's really exciting as we are wrapping up this mission that started back with some ground trials even last year and selecting red clover as our leguminaut that should fly, and then going up on NG-15 in February, being on station for 50-something days or so, while all of you were growing plants in your homes and classrooms and watching our 9 wonderful little seedlings grow in space. Isn't that exciting that we have something little green seedlings that were floating around in space and growing? And so we're gonna see now that they're back on Earth, what's happened to them. And we wanna have some feedback from you about what you think has happened so far. So Mr. Wilkinson will be joining us in just a couple of minutes, but to kick us off, let's have Tony go ahead and show the video of astronaut Shannon Walker.
Sure, coming right up. Can you see my screen?
Yes.
Okay.
So this was on April 25th. This is astronaut Shannon Walker, and she is removing the ExoLab-8 Cube Lab from the Space Tango locker. So you see that they have these cabinets and lockers of sorts that hold all different kinds of experiments. And so this is where ours was. You saw it turned on its side, and you can see a lot of the electronics and power sources, a lot of the cabling, and that camera is just over her shoulder.
I love things are just floating around, Lori. It's so cool.
It is floating around because that's how it's done in microgravity. You can't set anything down, and astronauts have to get used to that of when they have something in their hands, they can't just set it down unless it's Velcroed, otherwise it floats away. So we're going to watch her.
There's some funny stories of when astronauts return to Earth and they just want to put a glass to kind of just put it out there to float, and it falls on the ground. Muscle memory. Yeah, it does. It takes acclimating and getting used to being in that different environment. We kind of take it for granted every day that we have advantages with gravity, especially when we're watering our plants, right? That's a big concern. A big difference between ground versus flight is the water delivery. They don't use soil in space to grow plants. They use various growing media like we did. We had that kind of vegan jello type substance that we grew ours in, the agar. Hey, Lori, while the cabinet is open, I'll note you probably see these big circles in the back of the locker where we pull the cards out, and you could see that our lab was pulled out. Those are big fans, and they help circulate the air to keep things cool in our lab so they don't get too hot and our plants don't get all wilty. So that's just nice to see that when it's open. And there's a whole ducting system that works behind that. She just closed it off there, but just thought I'd mention that. Ooh, what do we see right there? Does that look like a Bitmoji?
That looks like Astromoji Lisa Turney right there, and representing from Linwood, Kansas. So she was our virtual teacher in space, selected to be the Astromoji for this mission. And so she's been leading her students, K-5 technology students, through this experiment. Wonderful. So that's our Cube Lab floating up in space. That was pretty exciting to see, don't you think? Yeah. So
Lisa just joined the our conference.
Who did?
Lisa.
Hello.
And Mike,
Oh, there's
Lisa.
Lisa.
got our VIPs popping in.
We were just watching you in space.
Oh, that's an awesome video. Loved it.
How did your students respond when they saw the video?
Oh my gosh, they were so excited. Some of the classes haven't seen it yet. I haven't been able to go into their class to show them. So they were like so shocked when they saw it. Like, wait a minute, that's you.
Wonderful.
Well, let me show the very last part again.
Okay.
While you are floating.
Floating upside down.
Are you sure you were upside down?
Well, oh, that's a good point.
Maybe Shannon's upside down there.
That's awesome. My school was so nice. They made everybody, all the kids have a button.
Oh, nice.
Wonderful. And now I see Mr. Wilkinson, Michael Wilkinson, has also joined us here. He's gotten to his lab there, and I believe you have some pretty exciting things to show us as well from some of the flight experiment images. You want to go ahead and kick that off?
I can, sure. So let me just share my screen here. Okay, whoever's hosting, I need to have
yes,
sharing permission. So while Tony's doing that, so reach over here, my little this actually this little teeny tiny refrigerator over here is NASA spinoff. So this is a refrigerator and incubator, depending on which you need it to be, and it's the same kind of system that they actually now have on station. You know, probably a little fancier version.
So it's very official.
Yeah. But so I thought it was very appropriate when I decided I was going to get for the lab in here to get something that was a NASA spinoff. So this is our flight tube. This actually is something that 2 weeks ago, 3 weeks ago, was on orbit. This is the slowest this thing has been going in how many weeks? It was going 17,500 miles an hour, and now it's going 0 miles an hour in my lab here. Probably very disappointed. You know, that whole need for speed thing. Let me just find my.
It's all relative, Michael. It's all relative.
That's right. We're still moving 1,000 miles an hour, right?
So just recall that the our flight experiment came down on the historic Crew 1 Dragon with the astronauts, the 4 astronauts, and it splashed down off the coast of Florida in the Gulf of Mexico on a Sunday. And then on Monday, our flight provider, Space Tango, was ready to hand off the tubes. So I went over to Kennedy Space Center and picked them up from them. And then we started evaluating the 9 seedlings and determined that this particular tube number 1, was kind of intriguing. Now we're still examining all 3 tubes. But tube number 1 had some interesting things going on. And so that's the one we decided to start with and ship off FedEx overnight and get it into Michael Wilkinson's hands.
Yeah, so
focus on today is this tube number 1.
So this is tube 1, and you might remember this is the one that we couldn't really see much on orbit because the media had shifted and it was in kind of a dark corner in terms of the camera. Apparently it was getting enough light for growth, but photographically we weren't getting enough light there to really do much imaging of it. So here we are, nice clean image of it. All 3 seeds germinated in this tube. We have you can actually see all 3 seedlings right here. One of them is just a tiny little bit of root and the cotyledon. The other one's a little more developed root system and a pair of cotyledons in the beginnings of its first true leaf. But one of these actually grew way beyond anything that we could tell was going on from the flight images. This this plant actually has 3 trifoils. So it's got its cotyledons, it's got a singlet, and the first, second, and third trifoil all emerged on this. And So if you recall, it was growing the wrong direction. So from this point, by the P by Pyrex here, this is photographed on a square centimeter grid, so just in for sense of scale. So right about that point is where we transition from hypocaudal going to the left, and root headed off to the right, and you can really see that joint between those two structures. And the hypocaudal, we had the elation because it started germinating and growing in the dark. But then once we kicked up the light intensity, the stems and leaves took a 180-degree U-turn, headed back toward the lights that were above, in terms of, so it's to the right in this image. But the roots stayed embedded on the edge of the media and didn't really, I mean, you can see they turned sideways relative to up via light. So there's just, all kinds of phototropism and gravitropism going on here. And when this arrived, I had Lori send it to my school because of when the FedEx was going to arrive. So I opened up the package to share with my students, and they did some sketches of it from an image similar to the one I was just showing you there. And, our tagline has been, got nodules? Well, at least my students and some of my science colleagues here think we may have nodulation. You can see and I did not tell my students. This is all independent observers. You can see these nodulation type growth. They're definitely something of interest in the root structure. Zooming in a little bit more here, you can really see the development of the trifoils. And for those of you that were watching closely, we know that it's really around the second trifoil. Once we get to that point, that's when nodulation occurs and could be very likely. You can also see that second seedling here a little better as well. And you can see there's a lot of development in that root, some root branches. So I'm actually curious and looking really closely at that one as well, microscopically, to see what's going on. But here on the root, so the X on the Pyrex go up, and that section of root right in here by this grid line has that reddish color that we associate with nodulation. And so there is some potential that's there. They're less than 1 millimeter in diameter. There's a close-up view of the growth of that plant. It was so exciting to see this. It's a shame we couldn't see it while it was on orbit, that there was this much going on there. But look at that, 3 full trifoils. They're very, very tiny, but they are trifoils. And the singlet is right here. Can you see my cursor, by the way?
Yes.
Okay.
Yes.
All right. So the singlet is right here, coming out of the node. We have our cotyledon, pair of cotyledons. That's what emerged first. Then the singlet, and then the first trifoil, the second trifoil, and the third trifoil is emerging right there. And then again, you can see that for scale reference, that line is 1 millimeter in length. Okay, so here's the area of interest. So in this section, this is about 1 millimeter long. So where's my metric ruler? So if you can see me on the camera, the distance between these little tiny lines, guys, on your standard ruler. That red line, that's 1 millimeter's length on the scale of the photo. In that section, there's definitely something going on right here on that root. And what we have to do is a series of microscopic images. I'm going to take really, really thin slices, as only 1 or 2 cells thick. So just paper thin, thinner than paper, slices of that root, cross sections. And then we'll add some stains to it, and the stains will react. They react differently with the root tissue and the rhizobial tissue. And if those are nodules, then we'll get 2 different colors of. Oops. No. Okay. This is a mature nodule from one of the terrestrial controls. So this is, you can see there's a big difference in what these look like. This is what we know nodules to look like. So the full nodule is about 1 millimeter to 2 millimeters in length. on clover, and they're little potato-like in shape. And I've done some cross sections of this that I will get stained, and we'll be able to share that with you all through our network, and so you'll have a control image to compare. And those of you that do the microscopy lessons, you can do that with your own specimens as well. So I don't know, folks, what do you think?
One of the things that we talked about when we saw this initial image was we started with an assumption, or at least I did, that the nodules were going to look the same as they do in our ground trials. And then I had to stop myself and I said, wait a minute, if it's been under the stress of space flight, and this has never been done before, how do we know what a nodule from space looks like?
Exactly.
We don't really know the answer to that yet, right? Because it could be different. The way the rhizobia infect through the root hairs, the shape could be different, the size could be different, the color could be different. So while we can use what we know from the ground trials as to what we know about nodules, we can't always make those same assumptions when it comes to the flight experiment. So we have to really observe what there is and dig deeper. Yeah.
Absolutely. And one of our hypotheses pre-flight was, because we're potentially dealing with an hypoxia, low oxygen levels in the roots, that the nodules could be significantly smaller. And here, just to kind of bring people back to our very early lessons and our very early broadcasts, remember that the nodule itself is a way that the plant and the bacteria work together to protect the bacteria from oxygen. These bacteria don't like oxygen. And so they live in an anaerobic and an oxygen-free state within this nodule. The plant seals them off, and when the bacteria are living freeform, they have a mucousy substance that they produce to protect themselves from the oxygen, from oxidation. And they actually, if you might remember that if we slice an active nodule in cross section, when that gets exposed to the air, it instantly oxidizes or rusts and turns red. There's a substance in there that's very much like the hemoglobin in our body, an iron-based compound that oxidizes with the free oxygen in the air almost immediately. So that's, this is all a protection. So to be continued. We'll definitely be doing a lot more imaging. This has been done as you can see, the flight tube has not yet been opened. We're still in the process of working through our whole choreography of exactly how we want to image these, and we've got 1 millimeter of length to get some little slices from microscope slides. So we've got to be really certain what we're doing there, and we want to take that very slowly. So just to preserve the quality of the specimens, we've kept all the flight tubes sealed up as we received them when Lori picked them up from Space Tango at Kennedy Space Center. They've stayed sealed. They've stayed at 3 degrees Celsius. So they're at a kind of stasis to protect them so they don't degrade. And that'll give us this buffer of time over the next few weeks into the late spring, early summer as we do this microscopic work. But this really sets the stage, folks, for Flight 9. Because we may have done what we tried to do in this demonstration mission. So now we'll fly again in August, 90 days from today. We're L-90 right now, today, literally, on my mark. Mark, okay? We got 3 minutes.
That's right. And so within, you have science experiments that fly to the station, we know, like with model plants, ones like Arabidopsis is a frequently flown plant organism that is very intensely studied. So red clover has not been studied to that extent. And so it's important for us to do a replication mission and try this again, because especially since we had 9 seeds, and we're so far only seeing this possible nodulation on one of the seedlings. Now we're still going to go in depth and look at all of them, but this is the one that looks most promising. I don't know if anybody remembers the name of this plant from tube number 1. It's not King Cobra. King Cobra was in tube number 2.
That's why I give them designations, because I can remember that. It's like my friends. They call it Node 2.
Okay, it was not Diana. Diana was that you're close. Diana was the one up stuck in the felt, and this is one that was down in the media. Does anybody happen to remember them? Yep, Ted's given a hint. So this one we named Dio. Dio. Spider-Man, nope, Spider-Man was in tube 3. And so this is Dio, who is the one that we are looking in depth at.
So it was named some of our headbanger crew.
Yeah, so that's a band reference, a music reference. So that's great. So we'd like to
question here, Lori, about the, would the next trial produce this? If the next trial were to produce the same results as from Gabriel, would that be considered more of a victory? It's a great question, Gabriel. Every experiment is a victory in science, and that's the coolest thing about it, is you can't fail at science. You always learn something. You're always able to observe something. So it's always a victory. What the next mission would be is if we can replicate this, that really gives us the proof that this is something that we can do in microgravity, and then all the potential that gives us in terms of producing a good food source for our space explorers and for making better farming practices here on Earth.
Absolutely, because we definitely want to use more sustainable agricultural practices. I shared a story, news story here recently with some of the teachers in the ExoLab group and on our Facebook page. I was recently over at Cape Canaveral and near the Indian River. And I don't know if any of you have been to that area of Florida, but we get a lot of manatees in the Indian River that come here during the winter. And the problem that we're having this year in particular is that the manatees are starving to death. And there have been a high percentage of manatee deaths. And it's being attributed to the seagrass, their food source, is not growing because of the excess nutrients from runoff. And one of the contributing factors is agricultural runoff. That chemical fertilizer, high in nitrogen and phosphorus, is contaminating the Indian River and other waterways here in Florida. So you have an unbalanced ecosystem and food chain. And when you have that disruption and you take away a food source for the manatee, then you're going to have consequences, and unfortunately a lot of manatee deaths. So we can see how change of what we do in agricultural practices here on Earth makes a big difference. So using biological type fertilizer like rhizobia, like legumes, to replenish our topsoil before they plant other crops. These are small things that can be done, but have ultimately significant consequences for the entire ecosystem. So keep that in mind. Like, we're not just growing plants in space. We are, and that's exciting, but we're also trying to really facilitate change here on Earth, and each of us can take action to help reverse the damage that's been done. So for all of you learning about legumes and nodulation and what it means to have a biological fertilizer, you're helping the manatees too. So yeah. I just thought I'd throw that in there because that was something that just
totally interconnected.
So
Evie asks, what would be considered a loss? Is there a certain amount of clovers that have to survive to consider a successful trial? It's a good question, Evie. Space science is slightly different in that it's so expensive to send experiments. Every trial is a success. The only failure really is if you lose your experiment on launch or something. There's a failure at that level. But as long as your biology or whatever it is your science gets to orbit and you're able to collect some data, that's a success. And it's learning about from that, what if it didn't grow, if these seeds didn't germinate, if they didn't nodulate, if they didn't develop the different leaves that we expect them to in their sequence. Then the big questions are why? What was the factor? What was the stressor in this environment that caused that? So that's why your ground trials are so critical, so that we've got a big baseline. That's where we need lots and lots of replicated data to be able to say, this is what's quote unquote Earth normal, right? So then with those 1 or 2 specimens that we are able to achieve growth with on orbit, we have something to compare to.
Hey, Michael, if I can, I also want to append what you've said there. And for everyone, we're growing these plants, but we're growing them in some engineering design. And one thing we do learn from a mission like ExoLab-8 is what type of habitat can we create that's more conducive to success? So as we noticed in tube number 1, it was kind of dark for us to see. So we're going to be making some changes so we can see all the tubes a little bit better. If we can adjust the lighting and do other things like that, if some of our mechanical functions, like the way the water might be deployed through those little tubes, or the way the fixative might be deployed, these are things that we can improve. With respect to the number of seeds, we flew 3 seeds in each tube on this last mission. And for mission number 9, we thought, well, more is better, right? So we're going to try to fly with 5 seeds in each tube, hoping that we can see more specimens that are successful. So when we think about our plants growing in this really unique experience, in this unique environment, not only are we thinking about the plant and the plant health and what we can learn from that science, but from an engineering perspective, how can we make that habitat even more reasonable for the plants, even though they're going through these stresses of space flight and of microgravity? And so that's a really great question. I just thought I'd put that emphasis on there, that we will continue to improve what we're doing on the engineering side.
And as you pointed out, the change that had been made in the Space Tango locker with the fans, right, and having that temperature difference. So we know that organisms have a range of tolerance in which they will grow and thrive, or they will die, right? And so even something as we would think as simple as a temperature differential, that can make a big difference in how the plants develop. And some of them are more heat tolerant than others. And so that's something also to consider when we try to grow different types of plants. You've got some great questions here. We may try to grow different types of plants in the future with experiments. Magnitude's flown a Arabidopsis before, cowpeas. We are going to stick with red clover for ExoLab-9 in August, and then we'll see after that.
Yeah, Lori, we've also grown purslane and wasabi and just quite a number of microgreens. So in chat, what would you like to see? In our next mission, we're going to be flying the Trifolium praetens, the red clover again. But if you could grow anything in space, what would you grow? That would be a great thing to know from you guys.
Yeah. Laura, you mentioned that different scientists have flown Arabidopsis several different times. So there's been some replication of that plant growth. But you know what, guys? Most of the experiments are one and done. That's kind of the nature of spaceflight. We have a very special chance with ExoLab-9 to actually refly the same experiment a second time, almost immediately. That's unheard of in space science business. So this is a really cool opportunity with ExoLab-9. A lot of tomatoes in here, different fruits.
Blueberries, I like that choice. Very high.
Good antioxidants, good vitamin C. So this is good nutrition. Here, these are all plants that are high nitrogen need in terms of their growth. So that kind of makes our work even more important to establish enough nitrogen to support those kinds of plants.
Absolutely. And watermelon, strawberries, tomatoes, a giant pea. Good suggestion. So you have to also take into consideration the size of these plants, and if they grow on bushes, or if it grows on a tree, or if there's a smaller dwarf variety, right? Because you don't have a large space to be able to grow plants on the International Space Station. it often has to fit within about this amount of space, right? You know, a little cube, a little rectangular prism. And so the plants have to fit within there. They often harvest them in veggie and in the advanced plant habitat before they even flower. So they have limited number of weeks that they grow them in. A good question about the effect of space on the nutrients. That is something that is also being investigated by NASA, is looking at how the nutrient content, proteins, antioxidants, all those micro and macro nutrients, and the levels and how they might be different than what's grown on Earth. Because it's important from a nutritional standpoint. Eventually, we are going to need to supplement the food for our astronauts when they're in space on long duration missions. On the ISS, they're right there in low Earth orbit, so we can send up these cargo resupply missions every month or so, and they can get they open the box and they get really excited when there's fresh food there, the apples, the oranges, a little bit of candy sometimes, right? But that fresh food makes a difference. And one of the returning astronauts, they were all commenting how much they really wanted a nice big salad when they got back. And so we have to eventually figure out how to grow all of these different plants in space and long duration missions on spacecraft, and then ultimately on the moon and Mars in a greenhouse, so that they will have access to these crucial nutrients, since the prepackaged foods often break down. So these are all great suggestions. It's a little harder to grow the ones that grow on trees, but they're looking at some biotechnology changes and some genetic engineering even to grow them in a smaller space. So nothing is completely off the table, I don't think, when it comes to growing plants ultimately in space or on a surface.
Yeah, some of these are really just engineering challenges. And so that's, people are asking about bringing soil and stuff. Right now, bringing soil and compost, that's not something we can do, because soil is a living thing. It's a whole community. It's its whole, it's its own ecosystem. There's way too many variables in that, and too many different living organisms in there that we can't get safety approval to send soil. So other people were talking about, moon and things like that. That's kind of, and why we chose red clover is something that will grow on just agar with no nutrients, and it grabs what it can from the air. But the process of growth, it's fixing the nitrogen compounds. It will decompose that. You can make it into a controlled compost along with whatever media is left, and then plant something else in there, maybe some more clover, build a little bit more growth media, so you're kind of producing your soil. Mix some regolith into it once you're on the moon or Mars, and then actually be able to have something you can grow those carrots or potatoes in that need a deep root volume to be able to produce much to eat.
So red clover can be eaten as a microgreen. Someone's asked about, it's not going to provide much food for astronauts, but you can grow it as what's a microgreen, and that means you're only getting it to seedling stage. If you're growing for microgreen purposes, you don't actually get all the way to the nodulation stage with that plant. Microgreens are typically harvested between 7 and 14 days. And so there's a wide variety of plants that you can eat just when they're little seedlings. And those are really good choices for during space flight. Because they don't take up a lot of space, they don't need a lot of growing room or extra nutrients. They pretty much grow hydroponically with water or in a growing media like our agar. And they're very nutrient rich, as well as they provide that texture and taste, right? Astronauts tend to lose their sense of smell and taste while they're in space, and it has to do with the fluid shifting in their body, right? We don't have gravity there, and so they have this upward fluid shift, and they get very stuffy. So if you had a cold before, or you have allergies, that's kind of how they feel. And so they want things that are flavorful. So we have chilies that are going to be growing on the space station this spring. And then they're looking at all these microgreens that are very powerful flavors like wasabi or daikon radish. And so having that extra flavor punch and then just the texture of having salad to eat, that makes a big mental difference and psychological difference and connects the astronauts back to Earth. So those are some important things to consider when we look at growing both microgreens as well as larger plants that produce fruits. So why don't we hold off on some questions and are we ready for our Ksc tour? Shall we get into that? And I'm gonna do a speed tour for you. If you have ever been to Kennedy Space Center in Florida, go ahead and type that in the chat and tell me what your favorite thing was that you saw while you were there.
You know, I do have to say that all the questions that has been coming in, they are really thinking about this now. You really got them going.
Absolutely. We'll
It's not just mental and taste, it's also the intensity of the nutrients in those microgreens. If you remember one of our previous episodes when Christina Johnson spoke to us, it's like some of the microgreens can be up to 40 times the nutrient level that would be in the mature plant. So, you know, you think of your big mature leaves and fruits and stuff in your leaf bucket in your salad. If the microgreens, one bite full of the microgreens has more nutrients in it than that whole bowl of salad does. So it's really dense nutritionally.
Very good, very good. All right, let me see if I can share my screen here with you. Let's see. Okay. All right, everybody see the screen? All right, we're gonna do our speed walking tour through Kennedy Space Center and hit some of the highlights of what's down here at Cape Canaveral, Florida. And so this is over on the Atlantic coast. And if you have watched any recent rocket launches of the Falcon 9 or the Atlas V that just went off a couple days ago, this is the visitor center that is just down the street from that launch, those launch pads. So this is where SpaceX has been launching the crewed missions, is at Kennedy Space Center. This is the entrance to it, and you can see the rocket garden just behind the entrance. Here's our rocket garden. It kind of walks through history, and you can see the different shapes and sizes of them. The newest rocket is right here. That's the Delta II, and that is a type of rocket that was sent up for the Spirit and Opportunity rovers that went to Mars. So that's a new addition. If you have been here years ago, that's something new you'd be able to see. You can also sit in a little capsule, the equivalent to size of what the Mercury astronauts sat. There's a great mural of the International Space Station and all the countries that are represented. And now we're gonna venture in and look at the rovers in the journey to Mars. Ultimately, when we go back to Mars, we're gonna need a very powerful rocket. The SLS is under development, but we're gonna have to figure out how to get humans there. Within the Journey to Mars exhibit, you can see here, this is the Pathfinder Rover. Look how tiny Sojourner was. This was the rover that was launched in 1997 and just a few inches off the ground, barely a foot off the ground. And sitting next to Sojourner is the mock-up of Spirit and Opportunity. And these were the rovers that were launched, the twins that were solar operated in 2003 and 2004. So they were pretty much identical, but they sent them to two different locations on Mars, and both were highly successful. Sojourner was actually only supposed to last for a week and lasted 83 sols. And then Spirit and Opportunity were only supposed to last a couple of months, and Spirit lasted 6 years and Opportunity lasted 15 years, which is pretty remarkable. I thought this was an interesting model here. You can see the lines at the bottom of the inner circle, and that shows what the heat shield looks like on these various spacecraft that come in. The inner circle is what you see. That's how large or small the Mercury heat shield was compared to the outer circle of what we're going to have for the new Orion spacecraft. And so they do heat up. You will see significant amount of heat as spacecraft enter through both the Martian atmosphere or back through Earth's atmosphere. Ultimately, we do want to design rovers for humans, and those are in development. And then here we have our mock-ups. You can see a huge size difference with both Curiosity and Perseverance compared to the prior rovers. So Curiosity is still operating on Mars, on the Martian surface. It's been operational for over 3,000 sols. It launched back in 2012. And now we have our newest rover, which is Perseverance. And in the background, you can see, let's see if we can get a better shot of it. Ingenuity is the little helicopter that was a science demonstration mission. And they've had now 4 successful test flights of Ingenuity. The Martian atmosphere is very, very thin. And so it's actually very difficult to fly on Mars. But they managed to do it and succeed with this little 4-pound helicopter. You have a lot of similarities between Perseverance and Curiosity. They are exploring different parts of Mars. Perseverance is in Jezero Crater, and we're particularly interested in looking for past signs of life. They hope that Perseverance will be able to take some soil samples and eventually do a sample return mission to Earth.
Yeah, Laura, all of the rovers and landers on Mars so far have been chemical geologists, robotic geologists. Percy is the first biologist. Percy is a biochemist. So the first data points that we potentially will get of any kind of biological signatures, not just the chemistries involved.
And ultimately, we have bots before boots. And so it will take both robots and humans ultimately in the exploration of Mars. And actually, just this last week, another country has successfully landed on Mars. China had an orbiter, and then it released a lander. And so I think it's got a little rover that's going to roll off the platform as well. And so up until this point here recently, it had only been the United States that had been successful in getting a rover or a lander on the Martian surface. And so now we have more countries doing that. So for all of you LEGO fans, I had to get a little video clip. This is the Spirit and Opportunity mock-up. Oh, I'll go back for just a second because you can see the Lego version. So if you have, about 10,000 or so Legos or more in your Lego bins, you can build the Lego version of these rovers. And I think that's really an important thing for you to actually do, of designing different rovers and landers. If you just had a bunch of Legos in front of you and you had a science mission, a goal you were trying to achieve, you can use Legos to help model and come up with ideas on how your rover or lander would operate. So there's a nice little Lego challenge for you, maybe for this upcoming weekend or maybe in your classroom. We're now going to go out. This is the bus tour that takes us on the road from the Visitor Center out to the Saturn V, the Apollo Center, to go back in time and look at lunar exploration. But this rocket right here it's very small, but that is the original Mercury Redstone rocket that really started our space program. And it's right there at the NASA Badging Center, which is where we picked up our flight samples. And along this bus tour, it takes about 15 minutes or so to go out to the Saturn V, but you go by the Vehicle Assembly Building. Now, this is an exciting place. This is where you can see those large gray stripes on the side. Those are the doors that lift up. And this is where they built and stacked the rockets, the Saturn V rocket for Apollo, as well as all the space shuttles were assembled in this building. And so in the future, the Space Launch System, the SLS, is being assembled in this building as well. There is the crawler, which goes about 1 mile per hour, that will be taking the rocket from the VAB out to the launch site. There's other private commercial companies now that have facilities out here, include Boeing, Sierra Nevada, as well as SpaceX. And so they are all working together with NASA to get flights, cargo, and humans into space.
So, Lori, just for scale, because people don't appreciate how big the VAB is. That coach bus that Lori was on can drive on the stripes of the American flag that was on the side of the VAB. That's how big that is. So just imagine those stripes on the flag, the red and white stripes, are the width of a lane wide enough for a motor coach bus to drive down.
And the blue part where the stars are, that's the size of an NBA basketball court. So it's quite large, but 11 stories. This building towers. You can see it across the Indian River. You can see it from a number of different places. It's very recognizable. There's no other building nearby that is close to the height of the VAB. And so when you start seeing, rockets being stacked, particularly the SLS, this is where all of that is happening. And they've got some initial components in there that they're already starting to assemble as they're preparing for the first launches of the Artemis mission. This is a new addition out at the Saturn V Center, is the Moon Tree Garden. So what they did is this entire center is devoted to the Apollo missions. And the statue there is of the 3 Apollo 11 astronauts. Type in the chat. I'm curious, do you know the names of the 3 Apollo 11 astronauts? Here there's Apollo 1, which unfortunately those astronauts were perished in a fire. And so we had a gap in the program, moved from Apollo 7 then to Apollo 8. And so it's a beautiful space outdoors that gives information about each of the Apollo missions. And so initially they had to test, right? Whether it wasn't just landing on the moon with Apollo 11, Apollo 8, 9, and 10, they were all testing this technology to see if they could get there to land Apollo 11. And there's those 3 astronauts there. Also, one of the Apollo 11 astronauts recently passed away. Type in the chat. I'm interested to know, did you follow the news as to which one recently passed away? And so all the way out to Apollo 17 was the last mission in the early 1970s, I think around 1972. And so we have not been back to the moon in a very long time. And so it's time for us to go back. And that's what the Artemis missions are about. And so we've had the first class of astronauts that have been selected to be part of the Artemis missions. And we're hoping here in about a year and a half or so, year and a half to 2 years, that we'll have some of those first test flights, perhaps uncrewed first, but then crewed. Once we go inside, the building was essentially built around this Saturn V rocket. You can see it is absolutely huge. And then the mission patches for each of the Apollo missions is hanging on the sides and the ceiling. So let me look at the size of those engines. This was the most powerful rocket ever built. And now I think SLS is probably going to take that title, but the Saturn V, they use a lot of the technology. We learned a lot of things from the Saturn V, but it is mostly fuel That's what the size is needed in order to produce enough thrust to overcome gravity and get off the Earth. Requires a lot of fuel. That's showing you the inside. It's very small, right? This is very confined spaces within the spacecraft. So you have this large rocket, itty bitty living space. So those are the different stages. So there's 3 stages to the Saturn V, and they have some great interactive features that show what happens during the launch. And so we'll take a minute and just watch that as we get liftoff. And it's what's falling off is condensation and ice, right, that have been frozen from the oxygen. And then as it reaches orbit, it turns the engines off, and then you lose these stages. Now, the Saturn V was not a reusable rocket. And so obviously very expensive to make a new one, all the components. And those pieces that fell off, those initial stages, would burn up in the atmosphere or crash into the Pacific Ocean, is the intent. Now, there are some rockets that launch and their rocket pieces don't always fall back to Earth. And that's becoming an issue with space junk, right? Accumulating in orbit around Earth. And here you see the Apollo spacecraft. Initially, that crew module had to separate, turn around, and dock with the lunar lander portion. And then they set off for their journey to the moon. Took them several days to get there. And so it was Neil Armstrong, Buzz Aldrin, and Michael Collins were our 3 Apollo 11 astronauts. Michael Collins stayed in orbit while Buzz Aldrin and Neil Armstrong were those 2 astronauts that went down to the lunar surface for the first time. Throughout the exhibits, they have a lot of artifacts, which are just fascinating to see and compare. This is the in-flight suit, what they wore while they were inside the spacecraft traveling. So this was Jim Lovell's in-space flight suit. And so you see it's not pressurized, but it's just mainly in kind of for hanging out kind of clothes inside. And it couldn't be really bulky either because they didn't have a lot of space inside the spacecraft. But you remember with Apollo 13, that's the one that we nearly lost because of an explosion within the spacecraft after they stirred the oxygen tank. And so they actually got very cold on board wearing those. Now compare that to an EVA suit or extravehicular activity suit. This is the suit that Alan Shepard wore for Apollo 14 when he went down to the lunar surface. And you can still see the moon dust on his boots, which is really fascinating. But it's a big problem too, because that lunar regolith, it's like a fine powder, like flour. And so it goes airborne once it gets inside a spacecraft and it floats around. It was getting within the metal joints of their spacesuits and causing problems. They did some testing on Neil Armstrong's suit, in fact, and it had gotten through several of the layers of fabric and it made cuts. Lunar regolith is very sharp, like shards of glass. And it was almost like static electricity. It was sticking to the suit. So spacesuit technology has to be improved before we can go back to the lunar surface, especially to live for longer periods, because this was just after a few hours on the lunar surface. These white suits didn't stay white for long. So if you're interested even in sewing or in fabrics, right, you could have a career in space too, because they need people designing spacesuits. In fact, I saw a job advertisement not too long ago from SpaceX. They were looking for someone to sew spacesuits and gloves. So you see with the Apollo missions, most of them were around the equator, that central portion of the moon. And the Artemis missions are looking to go more towards the South Pole because that's where there is water ice trapped in the darkness of craters. And where there is water, we can use that not only for life support systems, but also water can become hydrogen and oxygen, which can become rocket fuel. This is one of the lunar samples that they brought back from the Apollo 15. So this is a really good size moon rock. It is an igneous rock. And I think there's one more. Oh, maybe I didn't get it in there. So they have a couple of them, but all the Apollo rocks are very much protected, and they are owned by NASA. And so I know some schools borrow them. This is the lunar rover.
This was my dream car growing up, Laurie. I loved watching this car ride on the moon. I want one.
So the later Apollo missions were able to travel a little bit farther from the spacecraft in a lunar rover. So you can see there's not much to this car, very minimalist in order to fit size and mass within the spacecraft.
And that all had to fold up like a giant piece of origami and fit in a cube hole in the lunar lander.
Like your old Jeeps in World War II. Now the batteries are significantly improved. These were just lead acid, I think.
Yeah, I think so. And the lunar rover is still on the moon, right? There is still there's tools, there's trash, unfortunately.
Between you and Steve, Michael, I don't know.
We're gonna get there. We can hotwire that baby.
Well, that's the question. If we go back to the moon about protecting the Apollo landing sites, we will probably do it as the United States, since that's part of our history in those spots. But will other nations respect the history of those locations and sites and equipment that is still there? So this is the Space Shuttle Atlantis building. This is back over at the main facility, and this is the outside. I just wanted you to get a sense that with the shuttle, it had the main fuel tank in the center and then two solid rocket boosters on each side. And so this is Atlantis. There's a great intro video that they won't let us record. But if you do visit KSC, you definitely want to see the whole presentation and reveal of Atlantis. It's phenomenal.
I may or may not have cried like a baby when I watched that.
It did take off like a rocket and land like an airplane on the Space Shuttle runway, which is also at Kennedy Space Center. You can see the Canada arm there is the robotic arm. So the space shuttles were used to help construct and transport the International Space Station modules, as well as the Hubble Space Telescope. And the Canada arms were absolutely crucial in being able to maneuver and help the astronauts deploy those payloads. So you can see how large the cargo bay is.
Yeah, these are definitely the workhorses for the International Space Station. I just wanted to correct, I said lead acid batteries, and that was incorrect. So they were silver, zinc, potassium hydroxide, non-rechargeable batteries. They had 121 amp hours on them.
Very good. Good correction. So you can see the engines here, and those were fired for landing as well, but it did glide down. And I'm going to see if I got a good angled shot, if I can pause it. There's some people about. It's kind of hard to see, but you can see some different coloring in the reflection underneath the bottom of the shuttle. And all those little dark spots, I want you to imagine that all of these are like little tiles. Think of like individual Lego blocks, and each one is unique in size and shape, and they have a serial number with them. And so they had to all be inspected every time before the shuttle could fly again. And this was, unfortunately, there was damage to the wingtip during Columbia. And that's why it burned up and broke up when it was trying to re-enter the atmosphere, as there was damage to that heat shield. And that particular mission did not go to the International Space Station. It had a different mission. And so at the International Space Station, they would normally inspect the underbelly and the wings of the shuttle, and they didn't have the opportunity to do that on that Columbia mission, which we lost the Apollo 1 astronauts, we lost the Challenger astronauts on liftoff, and then unfortunately the ones from Columbia. So it's good to learn history of where we've been. And now this is just a little wrap up of where we're going. So this is a mock-up of the Orion spacecraft. This was an early test vehicle for Orion that they've now got that you can see. Same kind of concept with using the Apollo style shape. That's a model of what the SLS will be like. Another commercial provider is the Sierra Nevada, the Dream Chaser space plane. It's similar to the shuttle. It will launch on a rocket and then it will return to Earth as a glider. And they'll be delivering cargo to the International Space Station. And they're also developing their own inflatable habitat and space station. And so they'll have crewed missions as well. So this commercial exhibit shows you with Sierra Nevada, with Boeing Starliner is another company that is going to be taking astronauts to the International Space Station. A little more spacious inside than the Apollo spacecraft, but still quite small. So you've got to be used to those confined spaces within these spacecraft. This is the first Dragon. SpaceX Dragon spacecraft that went up to the International Space Station. This was the cargo Dragon. You can see that the shape, the angles aren't quite as extreme as on the Boeing Starliner. And there's some orbit dynamics and some math associated with that actually regarding the stability of this shape of spacecraft being a little bit different than what you see with the others that are a little bit more cone shaped, a little more angled. You can see at the bottom of that spacecraft, though, where the burn marks still are. If you look at the very bottom, so that heat shield out, so it was coming back in. And it is intended to burn off some of it, and that helps dissipate the heat rather than hold it. So there are many technologies that go into designing, building all of these spacecraft, all these different systems. And so that is your quick tour of some of the exhibits at Kennedy. And of course, farmers are wanted. We need all of you to become our future astronauts, engineers, teachers, mission control, flight directors, as well as the space farmers to operate those greenhouses. And so all of you have started your careers here with us with ExoLab-8. And we hope that you will continue on with us for ExoLab-9 and keep going with science experiments on Earth and in space.
Hey.
All right.
Thank you, Laurie.
If you have any questions, you can type them in the chat. I will have to look up how fast this Dream Chaser goes. I don't know the answer to that, actually.
Well, I mean, the easy thing is any spacecraft that's in orbit has to achieve 17,500 miles an hour, and we've got to achieve about twice that to escape the Earth's gravity if we want to go beyond Earth orbit. So there's, that's your kind of your baseline.
Yeah. On return, yeah, you could look that up. So Dream Chaser is the Sierra Nevada Corporation, SNC, and actually it will become Sierra Space. And so you can look up about the Dream Chaser. So you may have opportunities, all of you, to become astronauts, not just with NASA, but with some of these private companies that will be sending up research labs and even space tourists in some of these facilities. So there's a lot of potential, a lot of jobs, and a lot of exciting research that can be done. Fish, yes, they have sent fish to space and they have studied them actually as part of skeletal system studies to know what happens to the bones. So fish can survive in space. Developments that we need to get people to Mars. Life support systems are going to be crucial. Everything you need, you're going to have to take with you. So oxygen, water, food, everything that a human needs to survive has to be with them on that spacecraft, and you need redundant systems. You also have to protect them from radiation. And there's galactic cosmic radiation, which can do damage to the DNA in your cells, and it could cause cancer. You also lose muscle mass and bone mass in long duration space flight. And so we don't want them to get to Mars, land, and then not be able to get out of the spacecraft. So they will have to exercise, and they will have to probably do some weight bearing exercise to keep their bones strong enough. If you see how astronauts return to Earth and they essentially get carried out of the spacecraft, right? There will be no one there to help them on Mars. So they will have to be self-sufficient entirely. And that is a huge risk, absolutely. But it is possible. We just will use the moon as a proving ground for a lot of these technologies that are in development now. And that some of you will get to.
Yeah, and I just want to add, those of you people are here, oh, there's engineers and there's scientists and there's you know, the astronauts themselves. If you're somebody who likes to do logistics, just the organization of things, systems, and how you do stuff and choreographing tasks, think about it. All that stuff has to be planned out. So if that's the kind of thing you like, there's some crazy cool jobs in the space industry for that kind of work too.
Absolutely. Even interior design. If you like to think about how a space should be organized, if you're within a spacecraft or a space habitat, you've got to have multi-use of different like things that fold up, you know, tables that go up against a wall. How are you going to organize your very, very small space? Think of a tiny house, right? Where you're living with 4 to 6 people within a very confined space. How can you maximize the organization of it? What things would you take with you? What things do you leave home? What personal items are you allowed to take? Are you just allowed a tiny little suitcase of your own personal items? So organization, but that creativity. Another thing that is sensitive, astronauts are sensitive to, is orientation of when they're floating around, like which way's up, down, left, or right. So when they design the inside of a space, they try to give them visual clues so that their brain isn't confused. When your brain gets confused on orientation of where your body is, right, the proprioceptive, you have a tendency to throw up, right, and get space motion sickness. And so they use things like, what color is the floor? What color is the ceiling? How do you orient yourself so that it prevents some of that confusion? The dog, that is a good question. You know, Laika was sent up and unfortunately did not survive. There was a cat that went to space, Felicity, the cat, and survived. We have sent a variety of animals. I don't know if they're planning to send another dog. That might be a little difficult to manage on the space station. Let's see, other questions. What happens if you run out of food? Well, you have to ration your food. They keep track of it as to how much they eat. They have a tablet, an iPad, and they log everything that they eat, every packet of water that they use. They are monitoring their supplies. And so they would have to probably send an entire like equivalent cargo SpaceX Dragon or 2 ahead to Mars, land it, and ensure that food was there for them. Otherwise, you're like Mark Watney and rationing potatoes. So weight make a large impact on who can go to space. So there are criteria right now for astronauts, but they tended to choose smaller men, right? When they were doing the originally Mercury astronauts, they tended to choose pilots, right? Space test pilots. But now it's really changed. And so, but there are some general requirements. You don't want to be too tall, otherwise you're banging your head around, right? And so they do have some general parameters, but that's changed over the years. And NASA, every couple of years when they open up for more people to apply to be an astronaut, they often have amended the criteria. And then, of course, the commercial companies, they may have an entirely different set of criteria of who they're looking for being an astronaut. So don't self-select yourself out, right? Go for it, because they want people who are excited about space and passionate and willing to learn and willing to work hard, and all those kind of critical skills. They teach you, right, how to fix something, right? How to work this tool, how to go down into the big swimming pool in Houston and repair the station. They teach you all that, but they're looking for people who have a certain mindset, excitement, and passion about space and about research and the potential of human exploration.
And if you don't get accepted the first time, apply again. I know a couple astronauts, one applied, I think it was 15 or 16 times before he got selected for flight. Most astronauts don't get selected the first shot around. It's very competitive. So it's 2, 3, 4 times that most astronauts are applying. So if that's a dream of yours, don't give up after the first time. Keep trying. Find out what they're looking for. Take other classes, get new skills, and apply again.
And start early.
Start early. I will say that our perspective here about astronauts really comes from another era, right? We're older folks. You guys are coming into a new age of space, the commercialization of space. In fact, on the Discovery Channel, there's a new program that's going to be starting. What's it called? That's Who Wants to Be an Astronaut?
Be an astronaut.
Right. And so they're opening that field up. I'll put the link in. It hasn't started yet, but literally people are applying to become an astronaut. So maybe if you're 15, 16.
Don't tell Ted, I'm going to apply.
Well, I already knew that, Lori.
Have you had that conversation with your husband yet?
And your family?
I'm sure all of you support me applying, right? I can apply to go to space. Yeah. I'll do lessons from the space station. That will be so fun. Like, that's what I'm going to put in my proposal, so I can like teach and be with all of you.
And I'll just say that the company that's backing this is a company that many of you may not have heard of before. It's a commercial company called Axiom Space, AXIOM, kind of like you have an axiom or a proof when you start doing mathematics. It's your founding principles. And they will be adding to the International Space Station in the coming years. They're building 3 modules over the next 7 years. The next 2 modules they'll build are to extend the crew quarters because it's kind of cramped and a little old fashioned. So they're going to have room for more astronauts, which is going to be kind of cool. And the 3rd module they're going to be sending up is a state-of-the-art space research facility, right? So if we're talking about growing plants, maybe we can tell them how they can do it even better. Or maybe we're looking other kinds of investigations. You guys are walking into that era right now, which makes us all very, very excited. So, you know, keep in mind, it's all open. It's whatever you want to make it. And we're excited that you're joining us in these journeys.
Absolutely. And, you know, my parents' generation grew up on Apollo missions. I grew up on the space shuttle missions.
Wait, I'm in your parents' generation?
Oh. Yes, I am young. I am still young, people. But your generation, like, there's so many opportunities with all of these commercial spacecraft as well as NASA. And so watch rocket launches, watch the testing of the SpaceX Starship, right? Elon Musk wants to send Starship to Mars eventually, right? Learn skills that are important, you know, from sewing, or if you like welding, right? Like Elon Musk needs welders, like to get that Starship together. So if you like designing things, there are so many opportunities for you to be involved in some way in the space industry and in space research. And like, we just are so excited that all of you have been part of our mission and that we have collaborated together with all of you to grow some plants in space as a start. So Michael, do you have anything else you want to end with before we wrap up?
No, I just want to echo my thanks to all of your participation.
Oh yeah, that's right.
It's just so great to have you all aboard.
All right,
Michael, are you getting emotional?
Oh, we have a bunch waving to us. All right. I think we have some who are signing off. Thank you, everyone. And Michael, you want to lead us out with the final Legumes in Space?
Sadly, I don't have that microphone connected because I came in. I was stuck in traffic.
Oh, okay. Well, you can mimic it for us.
Thanks for joining Legumes in Space.
Yay.
Bye, everyone. Thank
See you up
you.
there.